Electricity Part 4. Equations and calculations involving voltage, current, resistance, and power. Electrical energy is an important form of energy, and it is present in several energy transformations in our daily lives. Energy is needed to do work, and whenever work is done, energy is transformed from one type to another. The law of conservation of energy states that energy cannot be created or destroyed, but can be transformed from one type to another. There are many different forms of energy. For example, gravitational potential energy, elastic potential energy, nuclear potential energy, chemical potential energy, electrical potential energy, magnetic potential energy, kinetic energy, internal energy, thermal energy, heat energy, sound energy, and electromagnetic energy. Gravitational potential energy is energy stored by a body due to its position in a gravitational field force. It increases as the body rises above the Earth's surface. Elastic potential energy is energy stored by a body due to its stretched or compressed state. Nuclear potential energy is energy stored in an atomic nucleus due to its physical state. Chemical potential energy is energy stored by a body due to its chemical state. Electrical potential energy is energy stored due to the position of electrical charges. This energy can be transferred by charged particles, for example, electrons in metal wires or ions in an electrolyte. Magnetic potential energy is energy stored by a body due to the alignment of magnetic atomic dipoles within it. Kinetic energy is energy possessed by a body due to its position. Internal energy is the sum of the potential and the kinetic energies of the particles, such as atoms, ions, or molecules of a body. Thermal energy is energy possessed by a body due to the motion of its particles. Increased temperature produces increased motion, that is, increased kinetic energy. Heat energy is thermal energy transferring from hotter to cooler bodies. Sound energy is energy transported as particle vibrations through a material in the form of a wave, while electromagnetic energy is energy transported as electric and magnetic field vibrations in the form of a wave, for example, radio, microwaves, infrared, visible light, ultraviolet light, X-rays, and gamma rays. Batteries transform chemical energy into electrical energy. Rotating coils in magnetic fields of generators transform kinetic energy into electrical energy. Photovoltaic cells of solar panels transform light energy into electrical energy. This electrical energy can then be converted to other forms of energy, such as kinetic energy in a motor, thermal energy in a heater, thermal and light energy in a lamp, and back to chemical energy if it is redirected into a rechargeable battery. Complete and closed circuits must be built to experience this transformation and conduction of energy. A circuit contains many components. A component is a part or element of a circuit. Components of a circuit may be a cell, a lamp, an ammeter or voltmeter, etc. Electrical components generally resist the transfer of charge, and therefore energy is needed to drive charged particles through them. Components of a circuit may be connected in series or in parallel. Series circuits only provide one path for the current to flow, while parallel circuits have more than one path for current to flow. Parallel circuits have junctions where the current divides and then rejoins after passing through branches. In circuits, voltmeters are always placed in parallel across the component, while ammeters are always placed in series. Voltmeters are connected in parallel with the component to measure the potential difference or voltage across it. The reason for this is because current diverges through the voltmeter, and this can alter the current going through and therefore the voltage across the component being investigated. Owing to this, voltmeters have a very high resistance to current to keep this diversion to a minimum. An ideal voltmeter has infinite resistance. Ammeters are connected in series with a component to measure the current through it. They must therefore have negligible resistance so as not to affect the current they are measuring. An ideal ammeter has a zero resistance. Whenever voltmeters and ammeters are connected in circuits, the polarity of their terminals must be considered, and this refers to their positive or negative ends. Hence, the positive end of the cell or battery or power source must be connected to the positive end of the ammeter or voltmeter, while the negative end of the cell, battery or power source must be connected to the negative end of the ammeter or the voltmeter. Calculations involving current, voltage, and resistance. In series circuits, the current is the same in every component in the circuit. However, the voltage splits up across the components in the circuit. And resistors in series are added, while in parallel circuits, current splits up across the components in the circuit. The voltage is the same across the components in the circuit, and in parallel, the reciprocal of resistance is determined where 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc., etc. The current across components in a series circuit stays the same, where the current registered at A1 will be equal to the current registered at A2 and will be the same current registered at A3. So if the current recorded in A1 is 0.2 amps, then the current in A2 and A3 would also be recorded as 0.2 amps. Hence, A1 is equal to A2 and A2 is equal to A3 in a series circuit. And if more ammeters are placed in the series circuit, the reading would still be the same. The voltage across components in a series circuit splits up, where V total will be equal to V1 plus V2 in this case. Hence, if V total is equal to 3 volts and V1 is equal to 2 volts, then V2 will be equal to 1 volt. The current across components in a parallel circuit splits up. A1 is equal to A2 plus A3. If the reading at A1 is equal to 24 amps and the reading at A2 is equal to 13 amps, then the reading at A3 will be equal to 11 amps. The voltage, however, across components in a parallel circuit stays the same. V1 is equal to V2, V2 is equal to V3. They're all equal to each other. So if the reading at V1 is 15 volts, then the reading at V2 will be 15 volts, and the reading at V3 would also be 15 volts. Resistance is a measure of the opposition provided to an electric current. It is a ratio of the potential difference across a conductor to the current through it, where resistance is equal to voltage over current. The resistance R of a conducting wire is proportional to its length and inversely proportional to its cross-sectional area. In short, fat wires, the conducting part has the least resistance. However, in long, thin wires, the conducting part would experience the most resistance. A resistor is a device that has resistance. The total resistance in a series circuit can be determined using the equation below, where R total is equal to R1 plus R2 plus R3. Hence, if R1 is equal to 2 ohms and R2 is equal to 5 ohms, and if R3 is equal to 10 ohms, then R total, or the total resistance of the resistors in series, will be equal to the sum of 2, 5, and 10 ohms to give us a sum, or total of 17 ohms. The total resistance in a parallel circuit is determined using the equation below, where we have 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus etc., 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 depending on how many resistors are in the circuit in parallel. Hence, if R1 is equal to 2 ohms and R2 is equal to 5 ohms, and if R3 is equal to 10 ohms, then the calculated total resistance will be equal to 1 over R total equal to 1 over 2 plus 1 over 5 plus 1 over 10. We find a common denominator, which is 10, and end up with 5 plus 2 plus 1 over 10. 1 over R total gives us 8 over 10. R total will be equal to 10 over 8, where it can be broken down to 5 over 4 to give us 1.25 ohms. Here's another example. 1 over R total is equal to 1 over R1 plus 1 over R2. In this case, we have two resistors in parallel. One is 2 ohms and the next one is 5 ohms. We find a common denominator of 10. You multiply the 1 over 2 by 5 and you multiply the 1 over 5 by 2. You end up with 7 over 10 equal to 1 over the R total. Then you transpose, you end up getting R total is equal to 10 over 7, which in decimal form is 1.4 ohms. However, in the case of two resistors, if they are in parallel, the following equation can be used, where we use R total is equal to the product over the sum, where R is equal to R1 times R2 over R1 plus R2. Hence, R will be equal to 2 times 5 over 2 plus 5, which gives us 10 over 7, which is equal to 1.4 ohms. For the relationship of potential difference of voltage to resistance for resistors in series, the following equations may be used. Based on the picture, VA over VB will be equal to RA over RB. And VA over V total will be equal to RA over R total. And VB over V total will be equal to RB over R total. When cells are joined in series, the total EMF is the sum of their EMFs. If you have three 1.5 volts attached in series, then the total EMF will be the sum of all of these to give us 4.5 volts. When cells are joined in parallel, the total EMF is the same as the EMF of one of the individual cells. So if you have three 1.5 volt cells, then the total EMF will be 1.5 volts. The parallel connection of cells allows them to last longer. If two cells are in parallel, their rate of reaction is half. This means that each cell will produce just half the current. Hence, if three cells are connected in parallel, each cell would only produce a third of the current. Comprehension. Let's look at the rules again. Again, in the series circuit, current is the same in every component in the circuit. The voltage splits up across the components in the circuit, and the resistors in series are added where R total is equal to R1 plus R2 plus R3, etc. While in parallel circuits, current splits up across the components in the circuit. The voltage, however, stays the same across the components in the circuit, and in parallel, the reciprocal of resistance is determined where 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc. If V total is equal to 2 volts, A3 has a reading of 5 amps and A2 has a reading of 3 amps. Answer the following questions. A. What is the voltage recorded on V1? What is the voltage recorded on V2? And what is the current recorded on A1? You may pause the video to answer these questions. The voltage on V1 will be 2 volts and the voltage on V2 will be 2 volts. The current recorded on A1 would be 2 amps. Remember, in parallel circuits, the voltage stays the same along the components or across the components, while the current splits up. So if you have 5 amps up there and the current splits across 2 of the bulbs, then, and you see that one has 3 amps, one is using 3 amps, then 3 plus something must give you 5, which is 2 amps. And moving on to the next question. If the reading on V2 is 24 volts and the reading on V4 is 13 volts, then what would be the reading on V1 and V3? You may pause this video to answer the question. Correct. The reading on V1 will be 24 volts. The reading on V3 will be 24 volts minus 13 volts to give us 11 volts since the lamps are in series. Next question. Determine A, the resistance of the parallel combination of lamps, B, the potential difference across lamp M, and C, the potential difference across lamp N. You may pause this video to answer this question. The resistance of the parallel combination of lamps would be equal to product over sum, because this is a special case of resistors. It's only 2 and they're in parallel. So we can use product over sum, where we have R1 times R2 divided by R1 plus R2. Therefore, we get 2 times 8 over 2 plus 8 to give us 16 over 10, which is equal to 1.6 ohms. The potential difference across lamp M will be 5 volts and the potential difference across lamp N would be 5 volts. Simply because it's a parallel circuit, hence the voltage will not change going across those two components. Next question. Determine the total resistance of each of the following combinations A, B, and C. So we have 3 different questions. You may pause this video to answer the question. For resistors in series, simply add all resistors present. So for A, we add in the 4 ohms plus 3 ohms to give us 7 ohms. For 2 resistors in parallel, the following equation can be used, where R total is equal to the product of R1 and R2 and the sum of R over the sum of R1 and R2. Hence, we get 6 times 3 over 6 plus 3 to give us 18 over 9, which gives us a total resistance of 2 ohms. And for the final answer, C, for more than 2 resistors in parallel, the following equation has to be used, where we have 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. We plug in the values of our resistors, which is 4 ohms, 3 ohms, and 20 ohms, all under 1. We find a common denominator. In this case, it is 16. And now we have 15 plus 20 plus 3 over 60 ohms. We get 1 over our total to be equal to 38 over 60 ohms. We transpose, we end up with 60 over 38 ohms. And we end up getting 1.6 ohms for the total resistance. Next question. Determine the total resistance of each of the following combinations, A, B, and C, if each light bulb has a resistance of 2 ohms. You may pause this video to answer these questions. So for A, the bulbs B and C are in series, so they can be added. So you just add them, you end up getting 4 ohms. Now that we have the total resistance of the bulbs in series, which is 4 ohms, the total resistance of the entire parallel circuit can be determined. Since bulb A and the total resistance of bulbs B and C are parallel to each other, the total resistance of the circuit can be determined by using the equation R total is equal to the product over the sum, which will be equal to 2 by 4 divided by 2 plus 4. That will give us 8/6 for an answer of 1.3 ohms. In the next question, in the next situation B, bulbs B and C are parallel to each other, hence their total resistance can be determined. We find that we can use the equation product over sum equal to 2 by 2 over 2 plus 2. That gives us 4/4 to give us 1 ohm. Now the total resistance of the circuit can be determined since bulb A and the total resistance of bulbs B and C are in series to each other. Therefore, the total resistance of the circuit can be determined by using R total is equal to R1 plus R2. Our total will be equal to 1 ohm plus 2 ohms to give us 3 ohms. And for the final question, bulbs A, B, and C are in series with one another, but they are in parallel with bulb D. The total resistance of bulbs A, B, and C can be determined by using the total resistance in series, where we have R1 plus R2 plus R3. Our total would then be equal to 2 plus 2 plus 2 ohms to give us 6 ohms. The total resistance of the circuit can then be found using the following equation, where our total is equal to the product over the sum, which is equal to 6 times 2 over 6 plus 2 to give us 12/8, which is equal to 1.5 ohms. Okay, let's get back to the lesson. Conductors are materials through which electrical charges can flow through. Metals, graphite, and electrolytes are types of conductors. Electric charge is a property of matter that can cause it to experience a force due to an electric or magnetic field. An electric current I is the rate of flow of electric charge, and the Coulomb C is the SI unit of electric charge. 1 coulomb is the electric charge that passes through a cross-section of a conductor when 1 ampere flows through it for a period of 1 second. The ampere is the SI unit of current. 1 ampere is the current that passes through a cross-section of a conductor when the rate of flow of electric charge through it is 1 coulomb per second. Q is equal to IT. This equation is used to determine electric charge, Q. It is a property of matter that can cause it to experience a force due to an electric or magnetic field. The Coulomb C is the SI unit of electric charge. If the number of mobile charge particles N is known, together with charge Q on each particle, then the total charge Q is given by the following equation below. Q is equal to capital N multiplied by common Q. Currents are the result of voltages. Under the umbrella of dynamic current, there is direct current and alternating current. Direct current is a current that does not change direction, while an alternating current AC is a current that repeatedly reverses direction with time. Here are some examples of different types of alternating current and direct current. Peak value is the maximum value that the current or voltage acquires during a cycle. The RMS value of an AC current or voltage is the value of the direct current or voltage that delivers the same power to a device. It is 70% of the peak value. RMS is an abbreviation for square root of the mean of the square of all values of current or voltage during each cycle. Alternating current is generally discussed in terms of the RMS value. For an alternating current or voltage, each cycle is represented by one crest and one trough on the graph. The period T is the time taken for one complete oscillation or cycle to transpire. Its SI unit is the second. Hence, the time it took for one cycle to transpire in the picture is 0.03 seconds minus 0.01 seconds to give us 0.02 seconds. The frequency is the number of complete oscillations or cycles occurring in 1 second. Its SI unit is the hertz, which is equivalent to per second, 1 over S. Hence, according to this, we know that one cycle is produced every 0.2 seconds. So using the equation, where frequency is equal to 1 divided by time, we have 1 over 0.2 seconds to give us 50 hertz. So 50 cycles are produced every second. In general, when AC voltage is being spoken, we are actually referring to the RMS voltage, not the peak voltage, since it is the RMS voltage which determines the power the device uses. This equation is used to determine electromotive force, EMF, and potential difference, PD, where V is equal to E over Q. Electrical components generally resist the transfer of charge, and therefore energy is needed to drive charged particles through them. The electromotive force, EMF, of a cell is the energy used or work done in transferring unit charge around a complete circuit, including through the cells itself, while the potential difference between 2 points in a circuit is the energy used or work done in transferring unit charge between those points. E stands for electrical potential energy. The SI unit of energy is the joule. V stands for electromotive force and potential difference. They have the same SI units, which is volts. Q stands for electric charge. It has the SI unit of coulomb. V stands for the electromotive force or potential difference. It has SI units of voltage, and it is the push that drives electric charge around a circuit or between 2 points in the circuit. We use the equation V is equal to IR. Anytime voltage increases, current increases, or if voltage decreases, current decreases. So it is directly proportional to voltage. Resistance, on the other hand, if it increases, voltage decreases. Hence, voltage is inversely proportional to resistance. This relationship is known as Ohm's law. It is so once the temperature remains constant. If a material is an ohmic conductor, a graph of I against V or V against I can be generated. Ohmic conductors produce a straight line to the origin of the graph. Metallic conductors are ohmic conductors. Aqueous ionic solutions like copper sulfate solutions and molten ionic solutions like sodium chloride are also ohmic conductors. They also produce a straight line to the origin of the graph. For conductors that obey Ohm's law, the gradient of an IV graph is the inverse of the resistance. Gradient will be equal to 1 over R, while the gradient of a VI graph is the resistance, so gradient will be equal to R. For a filament bulb, the following shape for the IV graph is generated. The filament bulb for some time behaves like an ohmic conductor for the part of the graph that is straight. However, when the filament starts to get too hot, it no longer behaves like an ohmic conductor, hence the curved parts of the graph. The reason for this is because as the voltage is increased across the lamp, the electrons are pulled in greater force and collide more vigorously with cations of the metallic filament. Their kinetic energy transforms into thermal energy, causing the vibration of the cations to increase. The increased vibration blocks the path of the electrons to a greater extent than previously, and the resistance rises. When the semiconductor diode is in forward bias, a small initial voltage is needed before current flows. When it is in reversed bias, conduction is almost zero. Metals, graphite, electrolytes, and semiconductors are able to conduct electricity. Semiconductors are materials that have electrical conductivity between conductors and insulators. However, they are beyond the scope of this lesson, but look at the table for examples. Examples of conductors include copper, gold, and aluminum. Examples of electrolytes include hydrochloric acid, sodium hydroxide, and salty water. While semiconductors include silicon, germanium, and gallium. Electrical power is a rate of transfer of electrical energy, where P is equal to E over T. Or power is equal to energy over time. Since E is equal to VQ, they can be substituted into the equation. And we have now P is equal to VQ over T. P will be equal to the voltage multiplied by electric charge divided by time. And since Q, electric charge divided by T, time, is equal to I, current, we can also get P is equal to VQ over T. The SI unit of power is the watt. 1 watt is equivalent to a joule per second. So power is equal to I times V. Additionally, when P is equal to IV, then it also has units of AV. The V in the equation P equals to IV can be substituted with IR given Ohm's law V equals to IR, where P would be equal to the product of the square of current and resistance. Since P is equal to IV and I is equal to V over R, we can substitute I for V over R and get V over R, which gives us V squared over R. And if energy is equal to power times time, where E is equal to PT, then we get E is equal to IVT since P is equal to IV. And E is equal to IR squared T when P is equal to IR squared. Additionally, E is equal to V squared over R times T when P is equal to V squared over R. Let's recap. Electrical quantities. Power has the SI unit of watt. Energy has the SI unit of joule. Voltage has the SI unit of volts. Current has the SI unit of amps. Charge has the SI unit of coulombs, and time has the SI unit of second. Important equations associated with electricity, and I would suggest that you take your time and write out all 18 equations. Comprehension. Define the following electrical terms: current and ampere. Then differentiate between the directions of conventional current and the electron flow. Current is the flow of charged particles around a closed circuit via a conducting path. An ampere refers to the current that passes through a cross-section of a conductor when the rate of flow of electric charge through it is 1 coulomb per second. Differentiate between the directions of the conventional current and the electron flow. For conventional current, the theory behind it is such that the electrons pass from the positive end of the power source and goes around the circuit, then re-enters the negative end of the power source. While it's the opposite for the electron flow. The electrons leave the negative terminal of the power source, goes around the circuit, and enters the positive end of the power source. Distinguish between direct current and alternating current. Let me pause the video to answer your question. An alternating current AC is a current that repeatedly reverses direction with time, while direct current is a current that does not change direction with time. Question. The charge on an electron is negative 1.6 times 10 to the negative 19 coulombs. Calculate the charge flowing during a lightning strike when a current of 75 kiloamps flows for a period of 2.0 times 10 to the negative 4 seconds. Answer. First, list what you have. We're looking for Q, but we have I and T. Convert kiloamps to amps and plug in into the equation Q equals to I times T. Remember the list of equations? Look at your list of equations and pick the one that matches your variables, okay? And then once you plug in your values, you should get 15 amp seconds, which converts to 15 coulombs. Now the next question asks to determine the time required for a charge of 2.4 kilocoulombs to be transferred through a component when a current of 2 amps flows through it. Again, list out everything that you have and make sure you convert the kilocoulombs into coulombs. Then you see that from your list of equations, you would be using Q equals to I times T if you are trying to determine time. Transpose for T. T is equal to Q over I, divide 2400 coulombs by 2 amps, and we get 1200 coulomb amps to give us 1200 seconds. Electrons of total charge 12 microcoulombs travel across a vacuum tube in a time of 3 milliseconds. Calculate A, the current in the tube, B, the number of electrons flowing across the tube. Pause this video to answer this question. Well, we have two questions to answer. The first one is to determine the current. And like I always say, list everything you have and then use your list of equations and pick the equation that matches whatever list you have. So we have the charge, which is 12 microcoulombs, which converts to 0.00012 coulombs. We have time in milliseconds, which needs to be converted to seconds. We get 0.003 seconds, and we're looking for I. Since it is QTI, we're going to be using Q equals to I times T. We transpose for I, and I is equal to Q over T. We divide 0.000012 coulombs by 0.003 seconds to get 0.004 coulombs per second, which translates to 0.004 amps. Now, to find the number of electrons, we have the charge, and the equation that deals with number of electrons would be Q equals to capital letter N times small letter q. Small letter q has a value of negative 1.6 times 10 to the negative 19 coulombs. Then, if we're looking for the number of electrons, we have to transpose where we get N is equal to capital letter Q over common letter Q. Once we plug in our values, we get 75 quadrillion electrons, basically. So that's what we can say. And also, the negative sign is ignored. Okay, it's ignored. Now, we have 5.0 times 10 to the 14 electrons flow through an electrical component in a time of 25 milliseconds. First, you want to calculate the total charge flowing through the component, and then you want to calculate the current during the 25 milliseconds. So we have all that we need. You may pause the video to try to answer this question. So 5.0 times 10 to the 14 electrons flow through an electrical component in a time of 25 milliseconds. We want to calculate the total charge flowing through the component. We write down everything that we have and what we are looking for. So we're looking for Q, we have N, and we have Q. Okay, great. So Since we have N and Q, we can solve for capital letter Q, and we get 0.00008 coulombs. Now the next question is asking for current, which is I. We found Q, and we have T, which is time, but in milliseconds. So we need to convert from milliseconds to seconds. Once we see that Q, I and T are related, as in the equation Q equals I times T, we transpose for I. We see I is equal to Q over T, where I is equal to 0.00008 coulombs over 0.025 seconds. We get the answer 0.0032 coulombs per second, which is equivalent to 0.0032 amps. A potential difference of 5 kilovolts exists across an electrical component through which a charge of 2 microcoulombs flows in a period of 500 milliseconds. Determine A, the current that flows through the component, B, the current used by the component, and C, the power consumed by the component. So it's a 3-part question. All you have to do again is list out what you're given. We have V, Q, T, and I. We have to always convert to our SI units. So we have kilovolts. We need to convert to volts by multiplying by 1,000. We have microcoulombs. We have to convert to coulombs by multiplying by 10 to the negative 6. And we have milliseconds. We have to convert 2 seconds by multiplying by 10 to the negative 3. We're looking for I. Now, the first question asks for current. We have Q, we have T, we're looking for I. They're related, and they're related by the equation Q equals I times T. You transpose for I is equal to Q over T. We substitute our values in, and we get 0.00004 amps. From there, we want to find the energy. We have volts, we have charge, and we see that energy is related to volts and charge by the equation V equals E over Q. We transpose for E, where we have E is equal to VQ, and we substitute our values for voltage and coulombs, and then we end up getting 0.01 joules. Remember, the SI unit for energy is joules. Then the last question asks about power. We see power is related to current and voltage via the equation power is equal to I times V. We have I, we have V, we can substitute, and from there we find that power is equal to 0.02 amp volts, which is equivalent to 0.02 watts. I want to thank you for watching another session, another lesson on electricity. I hope everything you learned today was understood, and if you still don't understand, drop me a comment or try the questions again or just watch the video again. Alright, best wishes. Thanks for watching.